Eric was working in Princeton with Lyon Page, and he wrote these amazing papers on helium recombination with Chris there. And then he moved to Chicago and is there now. He's been more than 2 years. And yeah, today he will be telling us some of his recent works, which are all related to helium in the cosmological setting. And yeah, we will, of course, he will be around until tomorrow, actually until Wednesday morning. So everybody should try to grab him at some point. Okay.
Thank you, George. So as Ian said, I'll be talking about some cosmological aspects of helium. In the middle here, you see a helium discharge cycle. I'll say more about how to see there later. This is based loosely on a couple of published works. So just to set the stage, it's thought that helium was produced in the first 3 minutes when the temperature reached the nuclear energy scale, which is MBAC. But obviously that scale, the newly formed nuclei couldn't have bound electrons. So it wasn't until sometime later when the universe cooled through its expansion that you could capture these electrons. And the first electron was captured with something like 20 kiloyear, which is the energy scale of 54 eV. And then at some later time, the nuclear able to capture their second electron. So this is where the story gets a little bit easier. And you know that the universe doesn't just cool through its expansion, but also that compact luminous objects form and they reionize the gas. So it's thought that helium was singly ionized at around a gigayear by the light emitted by the first stars. But that radiation was not of a hard enough spectrum to doubly ionize the helium. And it's thought that it wasn't doubly ionized until around 2 gigayear by quasars. And then at some much later date, we humans discovered helium originally through the orange transition in the sun, and then later discovered it was on the Earth through emission from Mount Vesuvius. I should say that those were primarily not primordial nuclei. So first I'd like to zoom into the recombination history of helium, and this is in redshifts, so these are the redshifts. And since it's going toward cooler times, and the universe is very hot, so this is the electron fraction for proton. The universe is very hot, both hydrogen and helium were fully ionized. And then, as I said, around 14 kiloyear, helium was able to capture its first electron. And then for actually, okay. Then for quite a protracted period, the vast majority of helium nuclei had almost exactly 1 electron. And then at some later date, around 100 kiloyear, they were able to capture the second electron. And the 2 curves you see here rely on the subtlety with helium-1 as opposed to helium-2. We'll say about that later. What people call recombination is often this area here, and this is where you associate the formation of this candy. So this is when protons capture most of the remaining 3 electrons. So before I get into helium, I'd like to just review the picture with hydrogen because it's a little simpler and carries over directly. But the basic idea is that you have protons and electrons, and something happens to them, and you produce the neutral species and emits a proton. So obviously, this reaction can go the other direction when the universe is very hot, where protons ionize the hydrogen. So as the universe cools, this is the thermodynamically favored direction. So if I were to just think about this naively, I can imagine an electron and a proton being attracted, and then the electron sort of falling onto the ground state of this nucleus. And if you work through that and see what happens, well, if you form the 1s state, you emit this photon and create it in vapor, and that can very easily go on and ionize another atom. So the net result is ionization again. So one atom may relapse to the state, but another won't. So even though this is thermodynamically favored, it's kinetically somewhat difficult through this pathway. So we know that neutral species form, so how is it they actually do? And the trick is to degrade the photons in this process to many photons which have individual energies less than ionization. And this happens naturally in both helium and hydrogen, just from the electronic structure. So this is hydrogen first, and here you can see the L sublevels and the energies of n equals 0, 1, and so on, and n equals 1. So the basic picture is that electrons start out in the free states and are captured onto excited states and then relapse to ground state. So the formation of the neutral state is really the rate that you can capture to the excited state here times the probability that they can even make it from the excited state to the ground state. And this sort of picture has been known since at least 1968. So once they're in this n equals 2 level, there are two ways, either through this 2s to 1s to photon transition or through the allowed line. And you see that this line, this is Einstein A coefficient, you see that it's really quite fast. You might think that any electron here could immediately relax to the ground state. So we can again look at that one, and if we look at this reaction picture again, well, you go from 2p to 1s plus you emit a Lyman alpha photon. And that Lyman alpha photon can very easily go on and excite another atom in this 1s back up to 2p. So again, you see that the net result of this is begin at 2p. So that pathway is again kinetically fairly difficult. So I call this the traffic jam. I think bottleneck is a more common term. But the big idea is one atom emits a photon, excites another atom. It relaxes, emits another photon, excites another atom, and so on. But again, we know that neutral species do form, and these have both been rather difficult pathways. So another thing you can consider is this two-photon transition. And you see that even though it's quite a bit slower, it turns out that because this one is effectively locked, that this contributes a comparable amount of information at the ground state. So that's one way you form the ground state. The second is to note that these atoms are in an expanding universe, and that if you emit this Lyman alpha photon, you can imagine that you emit it in a wing or somewhere where there's lower optical depth and it can traverse some distance and actually redshift. So you can imagine one of these things redshifting off resonance before it can excite this other atom. And so then you can have the atom sort of legitimately relax to one state. And this escape through redshift is similar escape. This has been known also this I would say classical result at this point. So the punchline really of explaining this processes is that the combination of the ground state is surprisingly difficult, and that rare processes and some unusual radiative transport come into dynamics. And just to show you how. Oh, sorry. Yes.
What's the main
I don't know that offhand. Do you know?
Something very short, very short.
I
never made the number myself.
Yeah.
I just remember, I think in dance paper there was something with something like.
Oh, was it?
Yeah. 10 kilo or something probably.
Oh,
That's like one.
Yeah,
I had the number 10.
In the core? In the, yeah. Okay. I have a picture later of that, but there's no scale on it, so I can't remember. So just to show you how important some of these processes are in the overall picture of recombination, let's go back out and look at just the hydrogen recombination. So at early times in equilibrium, it's ionized. If you were to say that the universe is kind of an oven, and you just write down the partition function for atoms you can ionize, you get the Saha equation. So as you turn down the temperature of the oven, they very rapidly reach the neutral state. But you see that in reality, including some of these more subtle effects, many more than I talked about, you get this much more sort of protracted history. And this has big consequences for the CMB. So Wayne Yu has a nice PLAS paper from 1995 showing what the CLs would look like if you just had instantaneous or soft. So instantaneous would just be dropping flat here. And you see that both of those look nothing like the CMB that we know today. So this is just to say that that combination can have a significant impact on the CMB. But obviously, we know it's at a much more nuanced level than either we can picture this today. I'd like to switch gears and talk about helium and apply some things from hydrogen to that. So going back up to the full picture, this is what I just talked about. And then at this earlier time, like we can consider how helium captured the first electron, and this is about 14 kiloyear. So a helium nucleus with one electron is basically just like a hydrogen. It has a charge, except so now you can multiply the energies by 4, the boundary rates by 16, and critically the 2 photon rate by 64. So in some sense, the singly ionized helium is a fast hydrogen atom. And you can see that play out in the recombination history when you compare the full solution, including all these effects, and just assuming solid steady state. You see that it's basically solid. So it turns out this stage of recombination is very easy to calculate, but it's also not especially important for the CMB because you see that this is well into the tail of the visibility function. Okay, so the much more subtle line, or the much more subtle recombination is to neutral helium, and part of that is just from the electronic structure. So when you have 2 electrons, you can either make a spin singlet or a spin triplet. And within those sectors, you have a pretty similar structure, except the triplet has no ground state. But you still have the 2s, 2p, 3s, and so on. So in the sort of singlet sector, you have the rate of 2 photon decay, you have a fast allowed line, and then you have a new line that's played out in the context of recombination by the Resonant only in 2005. This is the so-called intercombination because it goes from singlet to triplet, and it's also rather slow. So this is one which has so it's both fairly easy to treat, and this one has some interesting aspects to its rate of transport. So the picture that I showed at the beginning of the discharge lamp, the visible lines are all in the sort of 2 to 3 transitions. So these are all in the UV, obviously, that are sensitive. So if you look at the allowed line, a very similar thing happens where say one atom relaxes from 2p to 1s, emits a photon and excites some other atom. And you see that the net result of that is that you go from 2p to 2p. So again, this recombination pathway through the allowed line is kinetically rather difficult. I think it's informative to so this is where I should have had a scale. I think it's informative to actually look at what the scattering of these photons looks like in real space. So you know that photons aren't emitted in a delta function through these transistors, but absorbed or emitted in delta functions. And instead that there's some Doppler-Biden natural width. And so in the rings you can have a really long mean-free path, whereas in the core you have this tiny mean-free path. So if you look at this sort of scattering process in real space, you emit a photon, say in a tail, has a really long mean-free path, and then it scatters, say, closer to the core. This is where I wish I could get kind of scale. And then it's somewhere on the tail of the long mean-free path, and then over here is scattering more towards the core of the line. So the photons of this time trace this sort of interesting fractal pattern. And then at some point you can imagine maybe as this photon is emitted from this last atom, that it's somewhere, say, where the mean-free path is long enough that it can redshift off the resonant and then escape. So just diagrammatically, the picture that is that this photon, the universe is expanding, and this photon is redshifted off of this resonance.
But your scattering plot showed large distance between scatterings followed by many scatterings. Mm-hmm. And so this is involves some sort of shifting between the wind and the core.
Exactly, yeah. So you have some processes that,
Just really good explain.
Right. So this was all known as of 1968. And so now let's talk about 2 new effects that Chris introduced actually a number of years ago. And the thing to note is that this is a 21.2 eV photon, which can very easily ionize hydrogen atom. So this is greater than 2.6. And what that does is effectively destroy the photon so that it can't go on and excite some other atom. And this, I think, was proposed by Jim Peebles in the 80s, and then described somewhat briefly by Wayne in his 1995 paper. So we looked at this in more numerical detail. The basic idea is that you have some continuum opacity related to the abundance in the ground state and the ionization cross-section of hydrogen. So by destroying these photons and not exciting other atoms, you're accelerating recombination. The other effect we introduced was feedback, and the sense of this is that I said that this photon can escape from this resonance, but that doesn't mean there's some lower lying resonance that it can't excite. So say this, you've now emits this photon at T of 2000, it redshifts down to 21 eV, and at T of 1976 excites the recombination line. So these are all kind of coupled, and you should include those effects. So just to throw these together, this is the overall picture of recombination to neutral helium. This is you see is quite fast. This was direct fast as of a few years ago, which you see is quite a bit slower than soft. And this is where hydrogen recombination starts. And in this curve, you see the effect of adding the continuum opacity, and you can see that as soon as you get really any significant abundance of neutral hydrogen, you very rapidly speed up this process. And then by adding the feedback, the small dash line, you sort of slow down the chain. Does anybody have any questions about it?
So during that process, what fraction of the electrons are in balance states that are in the ground state?
That's a good question. I don't know that off. Actually,
Very small.
Yeah, very small.
so the way these impact, or the way this history impacts the CMB is that CMB photons photons scatter off of the electron population. And the matrix half-n is around, for those photons, is around 2.5 picoparsec. And the effect of this is to damp perturbations below a particular scale, and damping in k space with approximately as k squared over the wave number, or wave vector of the damping scale. And what that does in L space is damp this arm. And when I explain it that way, it sounds really kind of like how what you mentioned, the Poincare function of the beam doing as changing the arm out here, or similar sort of effective calibration. And the way I would advocate looking at recombination is really as a systematic, as something which you should just know the physics of and correct for the same way that you would do calibration and beam. So this is the change in the CMB from these two new effects that I described. And you see that it's getting to be a more than 1% on scale for the primary CMB. So this is only, as it turns out, about 1 sigma at the Fisher pictures level per Planck. So not so significant. But the recombination community, namely Jens here and Chris brought a Caltech, have been very active for the last few years. And there are a number of corrections to hydrogen now also. And all told, these bias the parameters built into Planck by potentially 2 to 3 sigma. And there have been 2 very nice papers published recently which describe sort of the full suite of corrections. And I encourage you to have a look at those if you're interested in sort of the cutting edge. So this has all been from the point of view of bias. So this is something which is, an effect which you think you know pretty well, and it's changing the CMB. But you can sort of turn that around and say, well, if the CMB is sensitive to this error, can you use the CMB to measure things in this error? And Todd and Hansen, I think, were the first to ask this, at least in this way, with the CMB. And here they say, well, what's one thing that the CMB would be sensitive to in this error? It's helium. So if you change the abundance by 10% from a sort of neutral value, in TT you get you change the silk damping in a really analogous way to what I'm showing here. In EE, you also see some feature for reionization, but unfortunately, whatever you can hope to learn here will be determined with what you how little you know about reionization. So at least for the near term, the best constraints I think will come from the TT sensitivity. So,
Sorry, what did you
In the 90s?
In the mid-90s.
Mid-90s, oh, okay.
For climate and etc. It was one of the standard parameters that got involved in calculation in very long run.
I should find that then. Adjust the so now we can change gears a bit and talk about going out and actually measuring the CMB and seeing what it has to say about helium. So we're talking about results from the Atacama Cosmology telescope. This is a picture of it at night, so you just want to see what's going on. I'll see that once later. So ACT is a large collaboration, and obviously a very significant fraction of the collaboration is here. And I worked on it primarily at Princeton. There are also a number of great papers out that I encourage you to have a look. And, not doing well with this. Encourage you to have a look and see if look at one towards right suit your interest. But I'll basically be talking about one plot from one paper. But you can find more about hardware, CMB, and estimate one sources in the literature. So just to review the telescope, it's at 5,200 meters in the Atacama Desert, and a 6-meter primary and a 2-meter secondary, which by virtue of fraction give it a 1.4 meter beam. And it has around 3,000 detectors in 3 different bands, which band has seen all. And so this is the telescope structure. You see there's a ground screen. You can't see much of it now, except for the very top. And you can see why the ground screen is there, which is that you don't want stray rays hitting these volcanoes. And then when you're at the site, there's a workshop in one of these containers, but it's completely self-contained. And this is a great plot from Amir's calibration paper. And what he's done here is combine the ACT anisotropes with WMAP, so you sort of get the best of both worlds. And if you wear glasses and you take them off, this might look like WMAP, and then put them back on, you can see that there's a lot of this sort of binary structure and clusters which you want to see well. So zooming in a little bit more to the instrument, this is before we deployed it. This was at Penn. You see the 3 windows. There's high density polyethylene with an anti-reflective Teflon coating, IR blocking filters, 3 silicon lenses with a sterilite center reflective coating, and then make a progressive holder until you reach these TDS arrays. And I guess I'm usually entertained because these lenses look solid black in optical, so it's interesting that they're transparent in a linear way. So this is a cross-section of the telescope. This is the primary, secondary, and then the camera. So I'm about this tall, so you can see it's really quite a large structure. If we now zoom in to the array itself, this is about 3 by 3 centimeters. And each one of these is a pop-up, pop-up detector with an absorber and then a small position edge superconducting sensor. So as I said, ACT is a large collaboration, so I thought I would just explain what aspects I worked on. So I worked on the housekeeping system and some of the things which interface with the control of different systems. And there are a lot of standard technical challenges which you can read about in this SBA paper. I'd say the most entertaining was that you can't run hard drives at 17,000 feet. So just how you save the data, and so the data were beamed down to on an RF link to a RAID array and measure. You can also see this may not be so ideal because it's covered in dust. And then
what goes on with marshmallows up there?
I'm sorry.
What goes on with marshmallows up there?
What we described is that there's a it's Bernoulli. It's something that keeps the heads off the pie, and the pressure to and so Mike has picked up the control aspect and made the Michael, I should say, and really made the thing sort of fall asleep for the last 2 or 3 2.5 years. It's also it's a fun place to work on the drive up. You can see llamas, and up higher you see they're sort of way up in the Grotrian. I didn't know what it would be like to work at 17,000 feet. Turns out it's rather boring. It's just a flat plane. I thought it would be precipitous drop off. You could just fall off planes. Not so exciting. So let's just dive into the results. So this is the power spectrum derived from the ACT data. And the power spectrum was derived in 2010 paper, and the parameters was derived in 2000. And this multiplied by L to the 4, which effectively lightens this because you're looking over such a wide range, especially in damping field. And so here you can see WMAP, obviously more constraining the large scales on the side. And then as you get to the small scales, you see ACT picking up the constraint. So one of the exercises you can go through is to say, well, what parameters would you be sensitive to out here, which WMAP would have been sensitive to down here? And you would find that the running of the scale spectral index, the number of relativistic degrees of freedom, the amount of helium, lensing, strings, and obviously above L3000 to something like 10,000, we can ask questions about Sinaitis-Lippich affecting clusters and point series. So I'll be talking in particular about just the result from helium. So this is lambda CDM with a YP of 0.24, and then you can see basically by doubling it, you reach something which is quite inconsistent with the ACT data. Now this is mostly just to say that you can constrain helium with the ACT data, but you shouldn't read off how many sigma that should be from this plot because of all the correlations. So before I show you the result for helium, I'd like to just briefly explain what the cosmological significance of measuring helium abundance even is. And there are two salient features with the helium abundance. One is that it's at the local minimum of the binding energy per nucleon. So if you look at it in the reaction network that forms the helium, most data prefer formation of helium-4 rather than the other species. The second thing to note is that there's a photon in this reaction. So we want to take neutrons and protons to make a neutron, which eventually lets you go through to helium. There's a photon, and because the photon to baryon ratio is so high, even though the deuterium is bound to 2.2 MeV, you have to wait for the universe to cool to 0.1 MeV for this reaction to proceed. So on the right here, you can see what happens when it does. So this is deuterium, and so this is there's no. So this is something like 0.1 MeV, and you can see that as soon as you start to form deuterium, you basically burn all of the neutrons into helium-4, and then some mixture of other species. So it's really so when you measure helium-4, you're really talking about how many neutrons per proton there were in the era before this. So we just take a step back to that. So this is what I just talked about at around 3 minutes. In this earlier era, if you look at the neutron-proton ratio at even hotter times, these will be in equilibrium with respect to weak interactions. So they follow this sort of Boltzmann suppressed law. So where protons are preferred by mass. And if they followed that, they would basically just you basically lose all the neutrons. But what happens instead is that because as the universe is expanding, these things can't find each other fast enough, and you freeze out some population of neutrons. The second thing to consider is that this time scale is minutes, and you know that neutrons decay. So that's this right end. So the question you really want to ask is, what's the neutron-proton ratio right here before this spraying process starts? And it turns out, with these calculations, that's about 2 neutrons per 14 protons. And just plugging that in, you get a YP of 0.25. So we should also note this process is sensitive to two aspects of the evolution history at this time. So the expansion changes how you freeze out, the abundance of neutrons you freeze out. And this is all radiation domination, so the thing which matters most is the number of relativistic degrees of freedom on top of the proton. So that will change the Helium abundance. And then in this part, we're actually burning to form the elements. Omega baryon has an impact, but much less so on helium than the others. Okay, so this is the result from ACT using the small scales. So on the there was a previous measurement from WMAP, and you see that the improved measurement in the silicon scale has tightened quite a bit. And for reference, this is BBN, assuming variance. So this is an interesting context where you can ask whether the recombination corrections that I described earlier are sufficiently converged. So those produce something like a 2% shift in the CLs at L of 2000, whereas the 1 sigma of this measurement is like a 7% shift at L of 2000. So that just means that at the level of these ACT data, the bias incurred by assuming the wrong recombination would not be significant compared to the error on Omega. So you can easily imagine that with future ACT data, SPTD data, Planck data, that you'll sort of saturate onto this sort of 2% level, and recombination calculation will matter. So Jens has run this number, and for cosmic variance at less than for L of less than 2000, you find that your estimate of helium is biased by something like 3 sigma if you assume the old version of recombination. So there's an interesting relation between between neutrinos and helium, and I have a supplemental slide if people like to learn more about that. But the basic point is that there's strong mutual evidence for both. So you both need neutrinos to explain the data and helium. So there are a lot of other ways to measure helium. The one I just talked about was through slope damping, and numerically the value from ACT is 0.313. But another way of getting at it is some of these are rather curious. Another way of getting at it is to measure deuterium in absorption. And this gives you a lower bound on the primordial buckets, which, assuming BBN, tells you the baryon to proton ratio. And then assuming BBN again tells you the helium. It goes one way. Another way is to measure baryons from the CMB, and this gives you a very similar value, assuming BBN. And then if you would like to actually go out and measure it without any assumptions about BBN, you can say, look at middle for extragalactic H2 regions, and you have to extrapolate to zero metallicity. So this has been confirmed by some schematic challenges, sort of creeping up for the last decade. And then you ask how well future CMB experiments could do, and it's something like 0.01 in YP. Does anybody have any questions about?
So the logical conclusion is that BBN and basically gives you helium to any number of digits. That therefore helium is considered to be known, and these things are just calculations are just testing recombination histories. That's the conclusion.
Oh, well, I guess there'd be different ways you could look at it. So you could say that this would be a direct measurement of helium out recombination, whereas this would be what you expect, assuming BBN. So testing maybe.
Yeah, but that's what it's kind of yellow about. I mean, this is
yeah.
But all the CFB without BBM gives you a 50 times bigger error.
Yeah.
So basically, you're saying that if you believe BBN, then you've measured helium perfectly, for all intents and purposes. And then using CMB, you would be testing recombination histories.
Yeah. Okay, so I'd like to step forward quite a bit to talk about a more recent universe and its reionization. So as I said at the beginning, sorry. So as I said at the beginning, it's thought that helium was only singly ionized at the same time that hydrogen was by the first generation of luminous objects. And it wasn't until some later date when quasars really turned on and reached the maximum space density that you could doubly ionize the helium. And for instance, some nice simulations to think about the radiative transport of the radiation from these quasars in the IGM. So blue is singly ionized helium at a redshift of 5. So this is assuming that you're following the first ionization. And you see that as these turn on, they also heat up the gas. So this is in temperature. And then in a way really analogous to hydrogen reionization, these regions sort of coalesce into more or less fully reionized or doubly ionized universe at some time around redshift 3. We also see that the effect of this is to make the temperature potentially very homogeneous. So it's interesting that this is at a redshift of 3 because that's something we can reach routinely in observation. So you could ask, well, would there be any way to think about this reionization process as sort of a high energy, or as a high redshift, as an easier, like sort of a hydrogen reionization light. So this is something at lower redshifts and at larger angular scales, where you might hope to do some sort of tomography or something which can tell you about the progression of this reionization. So the natural thing, well, you can say, well, we can use 2170 to do that, and the hydrogen's all ionized except within galaxies. But you could say, well, are there other hyperfine lines which would allow you to do this sort of tomography of that era? So just to sort of explore that, you can say, well, what do you need? You need the splitting on this hyperfine, this total quantum number, which is j plus I. And to do that, you need non-zero j and non-zero I. So if you look around the nuclei with non-zero I, you see there are about 115 of them. And that they all have some ionic states or states which have non-zero j. And the thing which is somewhat compelling about these species is that the spontaneous rate of all the transitions goes is each of 9. So you can imagine that even if some of these nuclei or these isotopic species are somewhat rare, then they might have strong enough transitions that you could do something with them. So I suggested to Matt that we look at helium-3+ as a potential way to probe this reionization the same way that people talk about probing hydrogen reionization with 21 centimeter. The argument for that is that even though its abundance is down by a factor of 10 to the 5 from hydrogen, which makes it sound impossible straight away, its Einstein A coefficient is 680 times larger. So that's a slight boost. The other factor is that this transition is at 9 gigahertz. So if you want to probe the reionization at around redshift of 4, you need to observe at something like 2 gigahertz, which is a much more comfortable observational range than hundreds of megahertz. So in fact, if you look at the sky temperature, the ratio of this curve to the sky temperature and these factors, you start to get something which is showing that it could be comparable to 21 centimeters. But there's some other considerations. So this line has actually been observed in the galaxy in H2 regions, and it's currently the best constraint on the helium-3 abundance outside of the solar system. So you could maybe imagine that if you could observe it in other galaxies, you could tell you something about that abundance. I think that's premature at this point. And it has been sort of thrown out as something you consider in a cosmological context. So we thought we'd think about this in a little bit more detail numerically with math simulations. So the first physical thing to consider here is that is the spin temperature. And it turns out that the radiative and the collisional coupling, which either couple the spin temperature to the matter temperature or the CMB, in this case are very inefficient because you have such a high Einstein A. And what that means is that unlike 21 centimeters, the spin temperature is basically the CMB temperature. So you can't really even imagine doing tomography with this particular line. So instead you have to, to proceed with it, you have to look in absorption. Okay. So there are systems where you reach, say, 100 times mean density, where you could imagine, well, obviously in ISM, where you can imagine emission from this line. But the picture of absorption is it's just like line alpha force. You have some, in this case, radiant bright quasar, and some blobs of gas on the intervening line of sight, and you get some absorption features. So we thought, so method is nice simulations, so we took lines of sight through them, and this is the optical depth. Except you don't have to multiply by a factor of 10 to the 6. So you see this is really quite a small optical depth. If you ask what sensitivity you need actually to measure some of this structure, it turns out you need something like a microjansky per megahertz. And that's obviously very challenging with present instruments. If instead you say along the same line of sight you have Lyman alpha, so you can find this sort of dense systems and you sort of match filter or sort of guide yourself to this structure, you need something more like 30 microjansky per 0.1 megahertz. And as a point of reference, people have achieved 100 microjansky per megahertz in OH studies at comparable wavelengths. But a big difference there is that rather than looking at a statistical detection over wide bands, they're considering a fairly narrow resonance. So I think the main challenge is with detecting this statistically would just be integrating down to it and then worrying about things like the passband calibration and RFI. So in some sense this looks a lot like RFI. Okay, another thing that we considered was the first allowed transition of helium-1. So this is this 584 Angstrom transition that I showed you in the context of recombination. And if you just work it out, assuming reionization equilibrium, you find that its optical depth is some small number times the thing you care about, which is the ionization fraction of helium-2, times some order unity ionization ratio, times the Lyman alpha optical depth. So you can imagine measuring Lyman alpha along lines of sight, which will saturate. I tell you something about dense systems, and then trying to pick out the first law transition. And again, we found that this one is well, it doesn't saturate, which is convenient for probing this era. It's also very weak. So just to run a simple number, we found that it will take something like 60 hours with costs on Hubble, the near UV part of that, given the group licensing. Now that's actually a little bit lower. So we think that this particular transition is also out of the current observational possibilities. So just to wrap up, helium has a rich electronic structure which gives it a pretty interesting history, but also one that you can know fairly well just through standard atomic physics. And the syntax in the CMB, and obviously to measure the parameters well in the CMB, you need to understand what's happening during recombination. But you can turn this around and say, let's use the CMB to measure helium. And I think that's neat because it tells you about the neutron to proton ratio when the universe is less than minute-volt. Then there are some good prospects for characterizing and actually even confirming the second reionization of helium. And I'd say goal there is to find unsaturated traces to that. And there are two possibilities, but unfortunately too unsaturated to be practical. So I'm happy to answer questions.
So, Molly said this, but I didn't get it clearly. Because you had what looked like a simulation or a cartoon to show the transition between regulation and ion, but there is an experiment or observation component that where people claim that they see the helium ionization effect.
Sorry for observation from whom?
Well, I thought that there were breaks or something that were showing that.
Yeah,
So
so
the current status of that is.
yeah, there's a number of blend evidence for the second reionization. So people, people have looked at the temperature in lemon alpha forest and seen the sort of increase, which you would say is consistent with the reionization. People have looked at metal lines and seen, I'd say, more anecdotal evidence.
And I recall there was something about proximity change. But what I'm trying to get at is, are those significant and strong indications that you can use that to place a constraint on the hardness of the radiation that's coming at high resonance? So that, when you say there's not much of a big black hole, injection of ionizing radiation, that's mostly
Yeah, I think that's a very interesting question.
I mean, that would seem to be something that the current effects on level right now.
Yeah, so I think the most direct way of learning about this right now is the lemon alpha transition of helium-1, and that saturates. So you may get a strong absorption of that, but there may not be hardly any of the single ionized species. But the thing you'd like to say is that there's a lot of the single ionized species up until redshift 3, and by knowing that, put a bound on how much hard radiation there was in earlier times. And I'm not sure how much you could say with the current knowledge of how far forward you have the single ionized species. But black holes or dark matter.
There's also a helium line from the 2s to 2p transition that people have talked about cosmologically.
Oh yeah.
Is that observable at helium-2 reionization?
Yeah, so I think in that case you have the Maxwell-Boltzmann factor for getting an n=2 state. Or maybe it's not Maxwell-Boltzmann, but I think we ran the numbers on that. The output actually is quite a bit lower than the first allowed condition.
So just a general question. Going through the whole reionization process, so does the helium reionization actually give the biggest thermodynamic input to the gas just because it happens? Well, you can see with no hydrogen reionization.
So put it together things which would change the temperature of the IGM.
Yeah, right. So the hydrogen, of course, it happens first, and then helium. This fire energy happens later.
Exactly, yeah, when you have the...
And you get more energy out per ionization event, but not that much in total, right? In fact, less you get, less in total.
But the entropy change is much larger during the reionization of iron gas. Like everything heats up about 30,000, 10,000 to 30,000 degrees.
One times the energy is 1/4 of the mass, so it's the same.
One ninth of them.
We're dumping that
Yeah.
energy much lower. Right.
Yeah, I guess we can go upstairs and discuss some of these. We will take Eric out for dinner tonight, I suppose, and I will then understand again.